Hello, Rusty.
Hi, Peter. How's it going?
How you doing?
All right.
Hello, Howard.
Yeah, how are you?
Good. How about you?
Not bad.
Do you know Rusty?
I do.
Yeah.
Okay, great. Hello, dear.
How are you?
Yeah, good.
Hi, Lydia.
Oh,
Rusty is going to be doing the electrical component.
There's more than electrical?
Hello everyone, and welcome to today's Middleton Group Masterclass session. My name is Steve, and for those who don't know us, Middleton Group is an Australian-owned and operated specialist electrical engineering organisation working across the power utility, renewable energy, rail, water, and heavy industrial sectors. Our organisation was founded with the sole purpose to work collaboratively with our clients to ensure the successful and sustainable delivery of projects. We're also firm believers in knowledge sharing, so we're here today to share our knowledge with you. This week's presentation will be presented by Scott Mitcherson, who will be presenting on HV earthing, where are the dead bodies? The presentation will run for approximately 20 minutes with 10 minutes open for questions. Just some conference room housekeeping if you like. Can I please ask for everyone to please keep your microphones on mute? If you have any urgent questions, please post it in the chat or use the Zoom's raise your hand feature. You can find it in the participants section of your screen. Or alternatively, you can wait till the end of the session to ask questions. Additionally, I will post a link out during the session to ask for your feedback. And I'll now hand it over to Scott. Thanks, Scott.
Thanks, Steve. Thanks for the introduction. Thanks for people attending too. There's a couple of famous names on there that I've enjoyed seeing. So that's good to see. So we shall begin. High voltage earthing. Where are the dead bodies? Now this is for the people in the trade will know this is not an unusual question to ask. Let's find out where they are. So first of all, there's a bunch of messages that I want just to take away at the end of this session today. So it's a bit of an insight into grey art of HV earthing. And also, if we could just make sure all our mics are on mute, thanks. So an insight into the grey art of earthing. Why do we do high voltage earthing? Obviously, as it says there, some safety, protection and operational. And we'll look at that a bit deeper later. Hazardous voltages, where are they? Wouldn't we like to know? So how do we find them? Another good question. And what is a safe voltage? So these are some dot points. As we've only got 20 minutes or half an hour, we'll go through these dot points today and we'll have some time for Q&A at the end, as Stephen said. So a few insights. Where are the dead bodies? That's, I guess, the question that people would like to know the answer. That's what drew you to this seminar. Well, statistically, I'm not aware that there's any dead bodies been attributed, so that's therefore electrocutions, attributed to a voltage that's been created on a conductive surface by an earth fault. So we're not talking about direct contact with high voltage conductors here. We're talking about voltages that are created due to an earth fault. You'd say in a switchyard or a substation out in the street. There was one case of a horse in England that may be attributed to causing a heart attack in the horse a few years ago. But again, to my knowledge, there's no actual electrocutions due to HV earthing or voltages caused by earth faults. So therefore, I've got to say it must be good engineering practice that we have achieved that zero result of fatalities. A lot of us go, well, at first it's safe, right?
Hold on a sec.
Well, perhaps not. Someone just helped me out there. The old Georg Ahnen back in 1827 come up with a very simple formula, and it's very good to use this simple formula in earthing. It reveals a lot of things. So let's say, for instance, we all would think that from a resistance point of view, something less than 1 ohm is pretty low resistance. In fact, 20 milliohms, as I've got in the formula there, is quite a low resistance. So if we have an earth fault of say 50,000 amps, which is pretty high, but it's not unusual, through a 20 milliohm resistance, we find we've got 1,000 volts. So it's a very low resistance, but due to the high currents involved in earth faults, we can have some pretty high voltages on fences, on HV equipment, etc. Perhaps even on the taps in your houses. But the good news is it's not for a long time. It's a pretty short time. HV faults are normally cleared in tens of milliseconds to perhaps up to a second. So it clears pretty quickly. So what are your chances of survival? Well, the probability of fatality is seen as being equal to the probability of coincidence times the probability of fibrillation. So breaking coincidence down a little bit, and we'll see this a little bit later, is that what's the likelihood that you or a person might be in contact with a particular metallic or conductive item during an earth fault. It's going to create a voltage on that item. And that's multiplied by the likelihood of fibrillation. So let's say your heart beats 60 times a second, that's once per second. And there's only a particular part of that heartbeat cycle, whereas if you're experiencing an electric shock, that may cause ventricular fibrillation. So there's a probability comes in there. So the chances of fatality are the combination of the coincidence and fibrillation probabilities. So as we asked earlier, what's the purpose of HV earthing? Well, quite obviously for safety of people. But secondly, for protection of the equipment. The earthing ensures that the fault current flows, so the protection picks up the fault and allows the circuit to be tripped. So we're protecting the equipment. If we don't, obviously all that energy is going to be dissipated in the equipment for a long period of time and potentially damage that equipment, or it'll catch on fire, burn to the ground. But earthing is also there for support of operational security. So on our electrical grid, we do expect the voltage to be within a certain tolerance and, of course, the frequency to be at 50 hertz. If we experience a large earth fault in part of the grid, obviously the voltage for that phase will be dragged towards zero. But when we lose that big load, if it's a huge load, a big industrial load, that'll affect the frequency as well. The frequency will go higher, losing the load off the grid, as you probably know. So the purpose of earthing is threefold: safety of the people, protection of the equipment, and also for operational security. Those three reasons are taken out of AS 2067. It was upgraded not that long ago. in 2016. Talking about standards, and we won't talk about them for long because they're a good cure for insomnia. AS2067 is a very common earthing standard to be used nowadays. It's backed up by a few other standards that are common to use. So we're not only looking at the voltages around substations, but also on our telecommunications equipment that can transfer voltages. We're also on metallic pipelines. There's plenty of pipelines around electrical assets that are conductive and can transfer dangerous voltages. So those references are in there too. Lightning is another study we do for earthing. Below that, you'll see a couple of earthing guidelines from E&A, EG0, EG1, good reference documents, and a few international standards at the bottom there as well. There are seminal documents that, if you follow the history, feed into a lot of those standards above. So that's enough of standards. Let's leave them behind. So hazardous voltages, where are they? Okay, so I'm not sure, you probably see my cursor. This is a typical switch yard, and we can see we've got a fault on the transformer across the bushing there. So now we've got an earth fault on this switch yard. And as we know, there'll be a resistance of the grid here. We push current through it, we create a voltage. And that voltage at the switch yard is known as our EPR, or earth potential rise. In the graph at the bottom there, you can see that top line. And that voltage is in reference to remote earth, or some point far away, kilometres away, where the soil is at 0 volts. Potentially the supply point for this switch yard could be at that 0 volts. So this switch yard goes up in volts to what we now know as EPR. And as you can see from the graph here, if we measure the soil voltage radially away from the switch yard, it drops further and further towards 0. And therefore, the difference between the voltage at the switch yard, the EPR, and the soil gets greater and greater. So where are these voltages? Well, we can measure these voltages within the switch yard between poles in the grid. Indeed, here is an indication of a touch voltage that this worker could be exposed to during an earth fault. If he's touching a conductive surface there, and the soil, his hand may be at a different voltage than his feet. We've got a fellow outside the fence here, and he's got his feet in contact with the ground. Indeed, due to the voltage gradient, there's different voltage from one foot to the other, and therefore there'll be a current go from one of his legs to the other leg. Part of that will go up and past his heart. We've got a maintenance worker over here that perhaps is servicing the earth or the sheath of the cable, an out of service cable, obviously. If there's a fault at the switch yard at the time, he may experience the difference in voltage. It's transferred through that cable sheath to him and his feet at the soil voltage. So quite a large transfer voltage there you'll see. Or indeed someone that's jogged along and they're leading on a conductive pole out in the suburb, and we find that that voltage is transferred to that conductive pole. His feet are at a different voltage, so he'll experience a voltage as well. So here's where we may find these voltages out at UGO poles or over unders, depending on where you are. On maintenance workers, inside or outside of the switch yard, or just people in the public that might be leaning on a fence waiting for a bus stop. They're all potential locations for hazardous voltages. This slide's just to show you the extent of, let's say we have a fault in the switch yard in the centre of this industrial area. We'll have cables that are connecting out to train loaders or out to ship loaders, out to other areas. All of these could potentially be bonding all of the earthing systems together. And if we have a voltage created at fault A here, that voltage can be transferred through all of these earthing elements out to other areas that are quite far away from the actual fault. As we've seen on the last slide, essentially the further you are away from the fault, the higher that voltage may be. So how do we find them? Well, one method we commonly use is the current injection test. And using this test, we can measure the earth potential rise that we've been discussing. And we can also measure touch and step voltages and compare them to the standards. So on your screen there, you can see that we've got the method, current injection test, commonly called the forward potential method. And what we have here is, and using Ohm's law, we've got a current source. We're going to move that current around the circuit. That includes the earthing system and the resistance of the grid of that earthing system. As we know from Ohm's law, we push a current through a resistance, will generate a voltage. So this is simulated fault current. We only push 5 or 10 amps around, as opposed to perhaps the 10,000 amps that will flow during an earth fault. So we're only going to create voltages at this substation under test, about 1/1000th in this case, of the actual voltages that will occur during an earth fault. Now, to help us do that, we run a temporary remote lead out, let's say, 1 kilometre into the field, and we just build a little temporary grid there with some stainless steel stakes in the ground, and that just allows us to get some good contact with the ground and push our test current around here. If we push 50 hertz, it'll just disappear. Our little signal will disappear into the fundamental. So we normally do off, or we always do off frequency injection testing. So 56 hertz is a common one that we can use. This way, with our frequency tuning voltmeters, we can measure the voltage on fences and of the soil. As you'll see over the left here, we can measure the voltage that we've created, the EPR that we've created at this substation grid, by measuring the voltage between the grid and this reference electrode out at remote earth or 0 volts. Indeed, to get those graphs that we've seen earlier, where it falls away from the substation, we'll take a number of measurements along the ground, potentially up to 1 kilometre away from the substation under test, to get a nice EPR curve rather than just a 1 voltage meter. So if we looked at where we can see the voltages and we've measured those voltages, what's a safe voltage? Perhaps just let me quickly go back to, for explanation reasons, back to our graph here. We mentioned it back then, but to put you back in the picture, we can measure voltages between the soil, where this fellow's standing, on fences, with our frequency tuned voltmeter. This is our forward potential that we measured, point by point. So we've set up our current, we've measured our EPR, we've measured our test voltages around here, our touch voltages. How do we know that the voltages we've measured on this fence are safe? We're using standard AS 2067, for instance, being a probabilistic standard. There's a nice bit of software called Argon that we can put in some inputs to the software, and it'll tell us what the allowable voltage is. So here's our allowable voltage down here. In this case, we'll look at the probability of coincidence, as we spoke about earlier. So what's the fault frequency? Obviously, the more faults per year, the more likely someone's going to be in a hazardous situation. The longer the fault is there, obviously, the more likely the person is going to experience fibrillation due to the coincidence. There's also some inputs over here for different contact scenarios. This one is for the MEN, so we'll talk about neutral situations, so taps in your house, etc. And we'll have a quick look at some different other situations on the next slide, but this software will tell us what touch voltage or step voltage or even hand-to-hand voltage that is allowable. We've got other inputs about soil resistivity. The higher the soil resistivity, the more insulation layers here. We've got surface layers. If you've got crushed rock or asphalt or concrete, this can increase the resistance of the circuit and therefore increase the allowable voltage for a given current that's deemed to be hazardous. So this bit of software here from our inputs can tell us what allowable voltage that the standard allows the designer to work to, and indeed that the likelihood of fatality is less than 1 in a million. That's what we aim for. Society accepts less than 1 in a million from a risk perspective. These other scenarios, we talked quickly about the MEN, so in your houses, at taps, etc. In your backyard, so fences, taps in your backyard, you're going to be there less likely, less times a year. So the standard allows for 416 contacts per year for a duration of 4 seconds. Urban, so you've got a conductive pole, say, out in your street, we're likely to be there less often than we are in our backyard or in our house. And indeed remotely, so high voltage towers that are in paddocks and in the bush, we're less likely we're going to be as well, very infrequent. So the less likely you're going to be in contact with a conductive surface that may be have a voltage created on it due to an earth fault, the less likely you are to experience a shock and the higher the voltage is allowed there. So in summary, so we're getting on here, in summary, HV earthing, just to answer, I guess, our objectives from the beginning. Hopefully we know a little bit more. So hopefully this is a little bit more black and white than grey. So happy attendees, hope you learned something. Why do we do the earthing? Again, it's for safety, so we've got a happy society. We have happy protection techs, the protection's working, and we've got happy system operators that don't have any frequency or voltage excursions that they can't control. We've also identified where we can find some touch voltages, and comparing them to that last bit of software, we can see whether the voltages we measured around the switch yard and further out on fences, we can compare that to the allowable of the standard and know whether they're complying or not. And indeed, if they're not complying, we can do some design work and do some mitigation. So hopefully we've got some happy Earth system owners at the end of this once it's deemed to be safe. So thanks for listening.
Thank you,
and I guess it's now to open up the floor for any questions.
Thanks, Scott. So yeah, if anyone has any questions, please feel free to post it in the chat or just come off mute or raise your hand. Yeah.
Scott Stewart here. You mentioned Argon as one of the software. Are there others?
That's the only, well, there are, yes. Argon's probably the more common one. There's some earthing software around, like seed eggs, if you've heard of that. Some of these softwares have calculators in them that you can pick a standard and put the inputs into them, and they will give you the allowable for that particular standard. I don't know that I've found any that have the Australian standard on them, generally from overseas, and they might use international standards like IEEE 80, etc. And of course, the formulas, you look up the standards, the formulas are in there. So I've seen plenty of Excel sheets generated from those formulas to do those calculations as well.
Thank you. Great presentation. Cheers.
Oh, thanks, Stuart. Much appreciated, mate.
Scott, it's Chris here. Thanks for the presentation. I just have one query. You've reminded me of a few terms I've forgotten, so that's good. Thank you. Regarding earthing, earth grids around trannies and lightning stakes and so on. When we're doing the testing on the soil, is there a requirement for the soil to be at a certain dampness, or do you have to wait after a certain period of time if it's rained significantly in the area?
Yeah, good question, Chris. Good
It's a little
question.
bit hazy as well.
That's a good question. You'll find that soil resistivity tests should be done when it's not wet. So a lot of utilities are required to wait a few days after rain before you test, because the moisture content is important. As the moisture content of the soil increases, resistivity will decrease. So if we test when it's drier, that's a conservative way to test. We'll get a higher resistivity reading. We'll get something that's probably representative of drier times. A higher resistivity reading, when you use it in your design work, is a conservative way to go. You end up needing a more extensive grid or more copper in the ground or other mitigation measures to ensure you achieve the low allowable volts in your design. So yeah, good question. Test in the dry, and we know then in circumstances when it does rain that the grid you've designed and installed is actually going to perform better when there's more moisture in the soil.
Yeah.
That answers your question, Chris?
Thanks for that. It does. Thank you.
Hi, Scott. Michael here. I wanted to ask about geological conditions, I suppose. Which ones would translate, say, a earth potential rise into a more dangerous voltage, I suppose?
Yeah, okay. I'll try and answer it with the basic geological knowledge that I've sort of, I guess, come across during my earthing time. I guess geologically, you can look up the expected soil resistivity of different types of soil, I guess, with, whether it's loam, sandy loam, whether it's rock, etc. So you find that clay and loamy soils are quite low. The more sand is actually quite high. Dry sand is very hard to get. Current to pass through, it's quite high. And indeed, granite, igneous rocks, etc., are higher as well. So I've found in my experience at hundreds of soil resistivity tests that down on your alluvial plains, etc., near water, especially near the seaside where you've got water table of salt water, there's a lot lower resistivities. And the further you go up the mountains, you've got more erosion of the soils off, you've got more rock exposed, and those higher up the mountain areas tend to be higher resistivity. And of course, with the higher the resistivity, the harder it is to design an earth grid to get your BPR down, your touch voltages down, and indeed there's a bunch of other methods to get into in situations like that where you try and contain the actual EPR. You might want to do what we call haloing, keep it very small and contained. And indeed, the advantage of a higher resistivity soil is that the voltage gradient drops away quicker. And that's an advantage in that means you're down towards 0 volts at the soil quicker, and so your contours of what your voltage will expose to pipelines and residences is more contained. So there's a few different methods. We try and bond it all and get a low grid resistance, a low EPR and low touch voltage. Sometimes that can't be done in high resistivity areas. So then we go the other way and we try and contain the current density. We have a higher resistance in the grid, which consequently lowers the fault current and helps us minimise the EPR that way. So good question. Hopefully I've exposed a bit of an answer for you there, Michael.
Oh, thank you. That was a very good answer. And thanks for the great presentation as well, Scott.
Much appreciated. Thanks for listening, Michael.
Hi, Scott. Andy Fitzgerald. Good presentation.
Thank you.
Just a question: when you're doing the off-frequency injection, 5 to 10 amps, you were saying, is that just directly scaled up to the actual fault current that you anticipate?
It is. Yeah, good question. Exactly. So I think, as I hinted there, if we indeed, for practicality out in the field, when you're testing, it's a bit of really an investigational test, and so it's nice to be able to, as engineers as we are, like to do things in our head if we can, and so if you know that your fault level on the grid you're testing is, say, 10,000 amps, there's some other criteria, but if you can push 10 amps around your circuit, you can very easily change your millivolts you're measuring on your frequency tuned meter. You can very quickly scale that up to real volts in real circumstance and know whether it's above or below your allowable touch voltage that you would have calculated before you start the test. So yeah, it's a direct scale, it's a linear scale.
Okay, thanks.
I think there are a couple of questions in the chat there, Scott. So first one from NG. What do you think about IEEE standard 80, which has been the most controversial standard in the history of IEEE? That is based on hand calculations and modelling is limited to 2-layer soil model. Should we opt for computer modelling instead of where we can incorporate multi-layer soil modelling, soil models like CDEX? Also, great presentation. Yeah.
Well, thanks for the appreciation on the presentation. Good question too. I think I can answer it fairly simply in saying that although being aware of IEEE 80 and being a bit of a seminal document, we tend to use the latest, obviously you use the latest standards. AS 2067 in Australia is a good go-to. Some utilities, some larger companies like to standardise on maybe EG1 or other standards. So we use what the client really wants. However, at the end of the day, just with the end of that, what was the end of that question, Steve, please?
Should we opt for computer modelling instead of where we can incorporate multi-layer soil models like CDEX?
Yeah, well, indeed, you use both. I mean, you use the standards to work out what the allowables are, and you use your software to model the circumstance or the grid that you're designing. And yeah, I've noticed there's quite a difference in using a software that can model 3, and in fact CDEX I think does 4, 5 and 6 layers, as opposed to 2-layer modelling. So it depends on the extent of what you're modelling too. With less layers, just with the 2 layers, if you read about the software you're using that's only using 2 layers, it should be able to detail to you what sort of errors you might find using that method. So be aware of the errors that can creep in to the modelling with 2-layer, but otherwise, yeah, a 3-layer is more accurate and less things to watch out for. The more layers, but you can get yourself pretty tangled up if you start to get into 4 and 5 layers. But it can exist that the models tend to take quite a while to run their algorithms. Obviously, if you've got 4 or 5 layers, so yeah, use the standards and use a good software with multiple layers of soil in the profile.
There's another question there in the chat for you, Scott, from Mustafa. In argon, the electrical footwear seems to have less resistance than the standard footwear for long fault durations, greater than 1 second. Any explanation to that?
No, I've noticed that myself over the last many years, and I'm not sure to me, it's just got to be the algorithm that's in behind there. You would expect that electrical footwear would provide you better protection, better insulation, better resistance than standard footwear, but I guess that's a question I don't really know the answer to. That's probably a question for E&A or whoever's, I'm not sure that they're still developing it. Sorry, I can't give a more defined answer on it. I guess the only thing I could say there too is to look at both of them and in your engineering be conservative. So is there any further questions, Steve? I can't see them in front of me if you'd like to.
No, I don't think there's any further questions in the chat. Rob Del Bianco just posted a comment. Good to mention that sometimes in high resistivity soils, you can get high EPR at 50 meters away from HV equipment, but the current available for shock is less than 10 milliamps due to contact area. I think it's just a comment from Rob there.
Thanks for the comment. Any other comments?
Any more questions, anyone? Okay, we might wrap it up there. Scott, if anyone has any more questions, I'm sure they can get in contact with you via email address or through Jack as well. And if you can just, everyone else, if you just take some time just to complete our survey, which I'll post the link of again. And this will just help us bring you more great topics like Scott's in future presentations. But thanks, Scott. Thanks for the presentation.
No worries. Thank you, everyone, for attending. It's been enjoyable.
Thanks.
Hope to do another one. There's a lot to learn. I can do another 10 of these. So I guess that's something if you want to put in the comments. Any further information or particular areas of earthing that anyone wants to hear about, throw them to us, and we'll see if we can pop another slideshow together.